I'm Lucie again. I work at SimilarWeb. I manage one of the data teams in the company here in Prague. It's amazing. And yeah, today I'm going to talk about anomaly detection and especially anomaly detection in time series data because it's an exciting topic that's rather underrepresented, I think. So let's get straight to it. What can you expect from me today? That's a good question. So basically, I want to give you a starting point. So we will talk about what anomaly detection actually is, why would you need to do it, how you can do it, and what libraries you can use to actually apply it in practice. And I'll also show some examples. Basically, this is meant to give you a leg up if you want to start doing anomaly detection on your own. It's by no means a all-encompassing and comprehensive deep dive into the field. That's not possible to do in the time that we have. So if you want to start, you will probably get some valuable info here. So yeah, let's get to it. And so the first question is, what is anomaly detection? So yeah, the definition is that it's a discipline where we try to detect some unusual observations. But what does it mean actually in practice? So usually when you have your data, your training set, you have some normal class in there. So for example, that normal class could be pictures of mobile phones, right? So that's what you've observed so far, how you've observed it, and that's the normal observations. What can happen that there can be also other types of observations. So maybe after a while, you will start getting pictures of mobile phones that just look different, right? One day somebody comes with a foldable phone and suddenly your model breaks. So those are so-called novelties, which are previously unseen samples that you haven't yet seen in your training set. And there can be one more thing, and that's actually outliers, right? And that's things that don't belong to the normal class at all. Those are the abnormal samples. For example, if you wanted pictures of mobile phones and you get pictures of headphones, that's a clear outlier, right? So there are two things that can happen in this case, and the outliers can already contaminate your training set. So you need to be aware of that. I'm sorry. But yeah, speaking about anomaly detection, it's also important to understand not just what it is, but also what it isn't, because anomaly detection is related quite strongly to data drift and its detection. However, those are two different concepts and two different things we need to tackle. Data drift is a change in distribution over time. So in the picture, you can see the mean of a distribution changing in different patterns. Whereas anomalies are data points, individual data points, that deviate from the normal data and the patterns that we observed, which means that in data drift, we see a change in the distribution. In anomalies, we see a deviation from the distribution. Of course, you will need different methods to detect these, and here we will focus on anomaly detection. But since these topics are related, I wanted to make sure that we all are on board in what we're talking about. And they're actually related through novelties, which is something that I already mentioned, right? Because over time, things change, distributions change, not only in time series data, but in everything. So if you were to collect the mobile phones over time, you would get a completely different distribution, completely different normal class. And what happens is that with your normal class from your training set, it can happen that you will observe individual distributions from the novelties first. Before you actually realize that there is a change in distribution, you need to update your normal class and maybe retrain new models. So novelty detection is one part of this, and it can be something that will foresee data drift for you in some cases. So it's important to distinguish these two. Here we will try to pinpoint the individual points, not really changes in the distribution themselves. So now we know what anomaly detection is, but the more important question, I guess, is what is it good for, right? Why would we do it? And since we are here at PyData, I suppose we're almost all data professionals one way or another. So we need it for observability, basically to be able to understand an internal state of our systems. And when I say system, you can imagine anything from a database to a human body, let's say, right? To give you an example, let's say that you have monitoring on a table and suddenly you will see that the mean of one column is changing drastically and you wouldn't know why. If you also employ other measures, not just monitoring, but maybe also anomaly detection, which is one of the things you can use, maybe you will see within your detection algorithm that there is actually an outlier in the data, which actually was the thing that moved the mean. So you can understand the why behind the problem. Moreover, you can be actually proactive. You can filter this data out so that it doesn't actually contaminate your database at all. I'm a data scientist originally, so basically for me, this means that I understand when I need to retrain my model. My models are more reliable and we have reduced downtime, which I'm sure all data people appreciate. But anomaly detection actually has much more use in the world than just for us, data people. There are many use cases, many of them. Let's start with security use cases. For example, you can have detection of fraudulent payments because those are anomalies. You could have some surveillance on intrusion detection, network security using traffic monitoring, all of that. There are many healthcare applications. You can monitor somebody's health using anomaly detection when your heart rate is something it shouldn't be. Probably you should see a doctor, right? So it's nice to be able to detect that if we are monitoring such things. It can help with diagnosing rare diseases. Also, since I think today is the official day of fight against cancer, today we have the apps that you can use to, for example, check a mole on your skin, right? And that's exactly one application of medical imaging where you can detect anomalies. So there is a lot of uses. We're going to focus on time series today, especially, but fortunately, a lot of the methods that I'm going to be talking about actually generalize to other types of data as well. So if you are thinking about anomaly detection in another setting, don't worry, you have different data. Some of the methods you will still be able to use there. And speaking of data, it's important to think about what data do we have, because there can be different settings, and you can probably guess what these three categories mean, right? So you can be in the supervised setting. Now, I don't know how about you, but personally, I never was so lucky that I would have all my data set annotated with all the normal observations and all the anomalies. That's the dream, but usually it's not what happens. What will happen more often is that you will work in the semi-supervised setting where you have partial labeled data. And that can mean that you have the normal class for training with no anomalies. That can mean that maybe you have a data set where somebody in a company manually flagged a few anomalous data points, in which case, if there's only a few, I'd recommend putting those in your test set rather than your train set. Or you can have any kind of combination of the two. But the most common case probably is the unsupervised setting, where you actually have no annotations whatsoever, and you just have to use the data to figure it out which of the points are the anomalies and which are not. It's, of course, the most challenging setting. Also, it generalizes to the other two. So if you can use something in the unsupervised case, you can also probably use it in the other two cases. So it brings the most challenges. That's what we're gonna focus on, because why not, right? What other challenges do we have here? The anomaly detection itself brings the challenge of having an extreme class imbalance, because anomalies by definition are events that are very rare, and class imbalance is difficult to handle as it is in its extreme case. Also, you can have trouble diversifying the anomalies from actual noise in the data that is no anomalies at all. The time series aspect of things brings some additional challenges, and that's that there are many types of anomalies that you can actually have in time series data. For instance, let's say temperature in the Czech Republic, that would be 40 degrees centigrade. That's a clear global outlier. Or temperature in the Czech Republic, that would be 20 degrees centigrade, but in January, that's a clear contextual outlier. And then you can have any kind of shape outliers. For example, you would have data with weekly seasonality and suddenly your weekend's missing. Where did it go, right? So That's time series data. Also for time series data, a lot of the algorithms are not directly applicable, which brings another challenge. And to make sure that it's even more fun, I added a multivariate aspect to it, which actually means that we can have multiple time series, because usually when you work with time series, you don't work with only one, but more of them. And they do interact. And when you want to detect anomalies successfully, quite often, maybe individually, all the time series will behave normally. But if you look at their combination of behaviors, that can actually be anomalous. Also, you can run into the curse of dimensionality. I will show you in a while. You can simply run into the problem of having too many dimensions. And then what do you do? So there is a lot of challenges, a lot of fun that we can have with anomaly detection, especially the case that I picked for the rest of the talk that you can generalize for unsupervised anomaly detection in multivariate time series, right? So how do you actually do that? That's the billion-dollar question. So first, I'll show you a trick. That's pretty much a bit of something like, feels like cheating a little bit when you use that. There is this library, and there are for sure more libraries doing this similar thing as this one, which is called the time series feature extraction library. What it does, it very simply and automatically extracts features from your data and transforms your time series data set into what is a tabular data set to get rid of the temporal aspect and all the challenges that that brings. This is great because it can open the door for you to use algorithms that are intended for tabular data instead of time series data. It has various type of features that you can use. It's absolutely amazing. And you can just use it basically as your first transformation step before actually detecting the anomalies. How? So I will be working with an example here, of course. And the example that I chose is actually stock market data. These are stock closing prices that are freely available on the NASDAQ website. And I just picked some companies that were on the home site. So we have 8 time series. We observe them daily for about 10 years. And we're going to try to detect the outliers there. So if I have this data set, how do I actually transform it? How do I get the features out of it? It's very simple. You can just do it basically in 3 lines of code with TSFEL. And I formatted the output so that it's more obvious. So for each of these series, we get 156 features, right, that you can use to detect your anomalies. Of course, this is when you might run into the dimensionality curse, because you might simply have too many dimensions and you might need to pick maybe only some of those features to check. Very easy, very simple. You can do it as a pre-processing step. But what do you put it in front of? One option would be some classifiers, right? I think basically anomaly detection naturally leads you to classification, especially binary classification, right? You want to identify what's the majority class, the normal class, and the minority, which will be a very small minority in this case, the anomalous observations. And you don't need to do that without the labels, which actually limits quite a lot what algorithms you can use, because most classification algorithms are intended for labeled data. One example, what we can use is an isolation forest. The way it works simply is that if an observation is quite often in the trees divided from the rest of the data at the very beginning, that observation is quite likely an anomaly, right? So that's what the isolation forest is going to do for us in this case. And it's going to directly tag the anomalies for us. How do you do that in practice? You combine it with the TSFEL library, right? Because isolation forest, of course, is not an algorithm that's designed to work with time series data. We have to do the trick, and then we can use it. Of course, you can use the application at scikit-learn to the rescue as usual. And you simply train your classifier, and then you predict from it. It's as simple as that. Here I'm working with a train test split, which makes it a bit more complicated. And the data you feed into it, however, is simply a sliding window in your features extraction. So you extract the features that I showed originally, not for the full data set. Here I used weekly windows, and there you train the classifier on a trained set, predict on a test set. It's not very complicated. The kind of result you can expect from this to show it on our data is something like this, and the blue parts are where it identified the anomalies. Here we can also see one disadvantage of this approach, which is that basically, since we are using weekly windows in the transformation, every point that the isolation forest detects as anomalous is actually a week of data. So if you want to pinpoint exactly where your anomaly is, you would need to have a follow-up algorithm after that. Nevertheless, for some applications, this is actually sufficient, right? And you can use it, and it's very simple. So that's one thing that you can use, a classifier, for example, isolation forest in scikit-learn. Nice. What else is there? There are clustering algorithms, which are amazing, especially in this unsupervised case, because they are actually unsupervised methods by their nature, right? So you don't need to figure out any workarounds or do some difficult selection. You will, however, need to do some pre-processing. So, for example, use the features extractor before you feed it into the clustering algorithms, because again, clustering algorithms are not designed to work with time series. One algorithm that you can use is dbScan, which is very useful because what it does actually is that it on its own detects outliers when you do any kind of clustering with it. It creates the clusters, and when it's not able to chain another point to a cluster, those points actually end up being outliers. So again, in practice, how do we do that? Similar as before, we use the features extractor with here a weekly window size, and you simply train your dbScan clustering algorithm and you predict from it. And what you get is basically a decision. What is the outlier and what is in the clusters that are considered normal. To be able to show it to you graphically, I used UMAP, the Uniform Manifold Approximation Projection. Amazing library. Feel free to use that anytime. Of course, here I'm starting with dozens of dimensions, and I'm just reducing it into 2 dimensions. So of course it will be distorted, so that's why the picture doesn't look that great. But for the points that it pinpoint, you can see that they are clearly far away from the rest of the data, which is good. It's always good to have a sanity check. This method, of course, will have the same disadvantage as the classification, because again, every point in here is a week. So you would need to either have an application where this is okay to have a window pinpointed instead of a point, or you will have to do a second step and figure out which observation out of that week actually is your anomaly. So that's the methods where you need some kind of pre-processing, and you can use the features extractor. But there are other methods where you actually don't need that. And one of them is reconstruction. And that's a very elegant method, in my opinion, because it uses simply dimensionality reduction and then reconstruction from the reduced space. What it means, you represent your data in fewer dimensions, and then using the inverse transform of the algorithm, you try to reconstruct it into the original number of dimensions. Perhaps if you see this kind of architecture of encoding and then decoding the data, you're going to think of autoencoders. Definitely you can use them. You can also use much simpler methods. You could use the UMAP library that I showed before, for example, where you can simply reduce the dimensionality using UMAP, then use the inverse transform. Or you could use the simplest dimensionality reduction, which is PCA, Principal Components Analysis. It's one, I think, of the oldest methods. It's a linear one. It has its advantages, disadvantages, but it's very simple. So I'll show that one in the example. And how do we actually detect the anomalies in this case? Well, it depends how the input and the output will differ, because the idea behind this is that for the normal data, the encoder will be able to capture the relationships and the patterns. But the anomalies are so rare that it will not be able to, so therefore the reconstruction in there will be most imperfect. So how do we do that practically? Again, it's a simple code in scikit-learn. This is the simplest one so far. You simply use PCA, you train it, and then you transform it into the reduced space. Here I used only 2 dimensions, and then you use the inverse transform method. Very simple. And in the graph below, I'm showing the absolute percentage error on each observation. And you can clearly see that there are periods and spikes where there are higher errors than other periods. So definitely, if you want to detect anomalies, that's where they're gonna be. Of course, PCA, I chose it because of its simplicity here, but it's a linear method. So of course, it's not gonna be perfect. That's why you are sometimes showing rather long periods where you would expect maybe some spikes, but other methods can do reconstruction much better. But it depends all on your data set, what kind of data you're gonna be working with, what kind of reducer you're gonna use. So that's reconstruction. And something related to reconstruction a little bit is forecasting, because in there also you can pinpoint every single point and decide if it's an anomaly or not. The advantage of forecasting is that it's a native time series approach. You don't need any kind of workarounds. You don't need any kind of pre-processing. You can just simply do it with time series data. The disadvantage is that it doesn't really come for free because you need to train your model, right? You need to have a good model first so that you can actually detect anomalies with it. Otherwise, it works very similarly as reconstruction. You will forecast and then you will check the error of your forecast. And where the error is largest, that's the supposed anomalies, because that's the pattern that is not in the data that the model wasn't able to train on. Here, I will stress the time series aspect of the situation, because in forecasting, it's not simply, you cannot do like a randomized k-fold with time series, right? What you need to do is to use either a sliding or an expanding window where your train and test set is moving in time to make sure that you always predict the past from the future. That's what forecasting is, predicting the, sorry, I said past from future. You predict the future from the past, of course. That's what forecasting is, this specific type of prediction. So what methods can you use? In the univariate case, like a typical algorithm would be our simple good old ARIMA. In the multivariate case, you can use vector autoregression, for instance. Of course, you could use much more complex methods like transformers, LSTMs, whatever comes to your mind. Just make sure that you always forecast correctly with your train and test set being in the right order. Practically, what library can you use? This time not scikit-learn, because if you've worked with time series data, you probably know that time series are quite underrepresented in the normal packages, but you can use skTime. skTime is a library that uses the scikit-learn API, but with providing you with actually the option to use time series models and all the algorithms related to time series. So what did I do practically? I used a sliding window. I trained on 4 months, tested on 1 month, and I had non-overlapping test windows. And you can simply import vector autoregression from skTime. It's a very simple package. If you work with scikit-learn, this will be no problem for you. Make sure you train on your train set, predict for the test period. And then again, I used the absolute percentage error in this case to compare the forecast to the observed values, but you could use any metric that's applicable best to your data. What are the results of that? You can see that it works better than the reconstruction in this case, because VAR is, of course, much better able to see the patterns in the data than PCA was, especially in this particular case of financial data. And again, wherever there is high absolute percentage error, that's where I would look at when trying to decide what the anomalies are. So you would set a threshold, let's say absolute percentage error is over, I don't know, 0.4. That's what's the anomaly. And again, it pinpoints exact individual points with the time series as well. Especially when you would have a period where there are no low errors, right? That would also ring a bell. So maybe you could not only have a threshold on the actual errors, but maybe on the minimal error over all your time series. That would also help you understand the compound effect that's happening in there. So those are 4 methods. I hope I explained them well enough for you to be able to work with them and understand them and apply them. What are the libraries that we can use? Of course, I showed already some of them. I showed you skTime, of course, scikit-learn, everybody knows that. The features extractor, which is very useful for time series, but there's one that's very relevant, I haven't mentioned yet, and that's PyOD, Python Outlier Detection. Apologies. That's a library that's designed for detecting anomalies in multivariate data. It's supposed to be very easy to use. You can detect outliers in 5 lines of code, as they say. But I think for you to be able to use it effectively, you need to have an understanding behind what you are doing. For example, if you do it via classification, what are the drawbacks, what are the advantages, and which of these algorithms you can actually use on time series data. So that's why I showed you the more detailed way in other libraries than simply using PyOD, because as an intro, that would not be very, very insightful, I think. But amazing library. It implements AD-Bench, which is a benchmarking paper for anomaly detection. They provide over 50 curated data sets that you can use if you just want to try it out, and like 30 detection algorithms. So definitely feel free to use that. One more thing, of course, we live in 2025, so maybe you have on your mind, yeah, but why would I do all that? Like, this is hard. Why wouldn't I just use an LLM? So yeah, my answer to that is you actually can if you want. Because despite the fact that LLMs are language models, they have nothing to do with time series and they're not designed for anomaly detection. Actually, there was a study last year that showed that if you compare state-of-the-art anomaly detection algorithms with the results of large language models, the large language models are actually only 30% worse, which I think is great if you think about the fact that they were not designed to do that. So you can use LLMs. It's great for some first and fast solutions, but you need to be able to understand that you will not be as efficient, right? I know that it develops. So in 2024, it was 30% off. Maybe it's going to get better in the future. Probably it will. But also it doesn't come completely for free because you need to do some prompt optimization before it starts working for you. You need to be okay with having a black box. And of course, you need to be mindful of the costs as always. So that's the overview of the methods from me. That was my last slide. I'm really sorry not to be there. If you want to catch up with me, you can add me on LinkedIn via the QR code. I thank you for all your attention, and I think that we can go to the Q&A.
Thank you very much. Now, can you hear us, Lucia?
Yes, I can.
Me, actually. Awesome.
I can hear you.
I was a bit afraid that we will have an anomaly in the communication and we will not be able to ask you questions. So that's resolved. Anomaly not detected. So the first question. We often use binary class, normal anomaly classes via RX XGBoost versus anomaly detection methods, OC, SVM, or LOF.
Here, yeah, or do we need microphone? No? Okay.
What is your go-to for initial experiment?
Yeah, so I think it depends what your setup is, right? So my initial experiment is always to do something baseline and something simple that you can work up from. So I would probably start with a simple version of the model and work my way up and see how it works, and that probably.
Thank you. Second question. How to correctly set cross-validation strategy for time series data? What are your recommendations?
Yeah, that's a great question. Thanks. I think that in time series data, it's if you haven't worked with it before, it's very specific compared to other types of data because you cannot use a k-fold that's randomized or stratified. You need to respect actually the direction in which time is happening. So I would definitely recommend either the sliding window or the expanding window. Usually what I would work with, depending on how much data I would have, but you can have the sliding window, for instance. I would choose a test window that's not overlapping. It makes your evaluation much simpler because every data point will have the same weight. And basically, that's what, if you have enough data, if you would be in the case that you wouldn't have enough data, you could use the expanding window also, which means that your training window is actually prolonging instead of moving together with your test window. And in that case, you can leverage more of your data for your training.
More questions are here. How properly set window size hyperparameter? How to experiment with its values?
Yeah, so it depends on which window you mean, if you mean the test window or the window for the temporal data. So if you want to do the features extraction, the important thing is that you need to think about you're going to have a lot of dimensions. And if you don't want your table to be wider than it's long, you need to make your window quite short so that you actually can have enough observations. Also, you don't want to have a long window because in that case, what would happen is that you wouldn't be able to pinpoint the anomalies, right? If your window would be a month, then which of those observations is your anomaly? You wouldn't know. So I think you need to start with this and then see how it works. I always say, let the data show us. So I always try a few values, or you can do sort of a grid search, right? And then you will see what works best when you evaluate, and that's what I recommend to use.
Thank you. Another one. Anomaly detection assumes that the latent space is continuous. It is not true in general for AE, if trained only with reconstruction loss. How about VAE? I hope the question is clear to you because I'm not sure about the acronym.
To be honest, it's not. Like, I usually use AE for absolute error, but this doesn't seem like that. I'm not sure if I've ever worked, to be honest, with time series that were not continuous. They usually are. So I'm afraid I don't know how to answer this question, honestly.
Yeah, usually I would just suggest to speak more with the drinks during the break. Not very possible today, unfortunately.
You can definitely ping me on LinkedIn, guys, if you want to discuss a bit more.
Yeah, that's perfect. Thank you. There's 4 more questions. Let's try to go over them. Have you ever used SVDD, support vector data decryption, in your practice for anomaly detection?
I did, but actually in my practice, it was never the method that in the end worked best. So it can be used, but I always found other methods superior.
Good. There's a bunch of forecast libraries, skTime, skForecast, Aeon, Nixtla. Have you tried others apart from skTime?
Yeah, I have, and I actually started doing data science before time series actually worked properly in Python, if you can believe it, in those ancient times. So I tried a lot. You can have a lot of ancient libraries, and it was a nightmare. I tried some of these as well, but to be honest, I quite like skTime because of its API that's similar to scikit-learn, and it's super simple to use and it's foolproof. So that's my go-to library.
Okay, thanks for the suggestion. When addressing based on the error, how do you differentiate between anomalies and your model being poop?
That's a great question. Of course, for when you prepare graphs for a talk, you don't really spend 3 weeks optimizing your models, right? In practice, you do. So you need to make sure that the error of your model is something that you find acceptable in general, right? So if you are looking at, if your measure would be, let's say, absolute percentage error, You check the mean, you check the median, right? Is that a model that's good enough? Is that an error that's acceptable in your case? If yes, and overall the error is low, then the points or the error in the individual observations is big. That's your anomalies. But again, you need to make sure that your model is good enough. And that's why actually the forecasting method is kind of costly in human time, because you need to have a good model before you can actually start detecting anomalies with it.
Thanks. So it was really interesting to have that many questions, and it's awesome to be the last one. Once an anomaly in the time series is found, how would you proceed if I'd like to know which of the features present or not present in data do explain this anomaly?
Now, you mean the features from the features extractor, for instance, right? I suppose.
I don't know.
Is
So here the author has been lost.
Doesn't matter. I'm gonna answer anyhow. Basically, I'm sorry. Basically, usually depends what method you are using, right? So if you are using methods that use all the dimensions and inputs, you don't really see that. It depends on the model. Some models you can actually reverse engineer how they are making their decisions. And in that case, you could decide on which dimension in either the original data set or on which feature it happened. Some models, they just don't give you this insight. And that's something you should always consider in data science, not just in anomaly detection. The trade-off between like explainability of what your model does and why it predicts what it does versus what it doesn't. So it depends greatly on the algorithm. For some algorithms, you can do that. For some algorithms, it's not possible.
Thank you very much. And I think we should really thank you a lot for, taking this extra effort to doing the presentation online, especially if you don't feel perfect. So thanks a lot. Let's give Lucie a big shout.
Thank you, everybody. It was great talking.